So I could see the similar lecture slides during my first year, and the lecture slides are actually adapted from as I mentioned, first year undergraduate lecture course, which is delivered by Professor Jonathan Burton, and you can find the full version of those slides over here. The lecture course is called Introduction to Organic Chemistry. So that's how you can find it. In terms of any textbooks that you might want to follow, usually at Oxford we recommend Organic Chemistry by Jonathan Clyden. But I would find Organic Chemistry by John McMurray much easier. And in fact, that was the book that I used to carry me from a A-level sort of, well, I would say very limited A-level knowledge up to the first year university knowledge. So if you are interested in the topic, in elevating what you know in chemistry, Organic Chemistry by John McMurray is well, I think the best choice. However, also the majority of organic chemistry textbooks will have good chapters on the topics covered by this workshop. Right, so let's just start on with how would you think in general about one of the simplest organic molecules, methane. So I'd say most people would draw methane like this. And it's not, in fact, what we like to do as organic chemists. So the shape of methane can be determined by VSEPR, which is valence shell electron pair repulsion theory. It's going to be covered by your A-levels and also during the inorganic lecture course at the first year of university. But in general, this theory says that the geometry of molecules is determined by minimizing all interactions between its electrons and bond pairs. In methane, we have four bonding pairs of electrons, and we have no lone pairs in this molecule. So we only consider bond pair repulsions, which lead to a tetrahedral structure of methane. And it comes, the tetrahedral adjective comes from the fact that those lines indicate a tetrahedron. And tetrahedral is just the adjective coming from that. Right. The important thing about this structure is the angle between two bonds, which is 109.5 degrees, and we call it tetrahedral angle. Interestingly, in methane, we also have a, oh, it's not showing up. Okay, let's see what I can do. Perfect. Interestingly, in methane, we also have the bond length of carbon-hydrogen bond length is 1.09 angstroms, where angstrom is 10 to the minus 10 meters. So it's quite a similar value to the 109.5 degrees. What happens though when we have something a little bit more complex than just methane? If we consider an ethane molecule, then perhaps you could try drawing it like this. So what you can see is that the tetrahedral angle is conserved even if you have larger molecules. So you could see that drawing methane took quite a while. Drawing ethane was just a lot of labor, and I can't imagine representing all my molecules in organic chemistry this way. So what organic chemists do is they draw skeletons of their molecules. And what skeletal representations are? Well, for example, if you think about a molecule of ethanol, it takes quite a while to draw. Then with skeletal representations, what you can do is just draw it like this. It's probably 3 times faster, much more efficient, and I think also it shows the hydroxyl group, which is the functional group in this molecule, much more clearly. So yeah, skeletal representations allow functional groups to be clearly seen, and those are and the functional groups are where the molecule is usually reacting. So general guidelines for drawing your skeletal structures is to draw chains of atoms as zigzags. So when you're going above ethane to propane, for example, you go like this, then butane, pentane, and etc., etc. So you can see now that the end of the chain means CH3, and the corner means CH2. So it is applicable in general when you can see just a carbon with 2 bonds, you assume it's a CH2. If you see a carbon with 1 bond, then it's a CH3. If it has 3 bonds, then it's a CH. And if there are 4 bonds, then it's just C. It also applies to double and triple bonds, so alkenes and alkynes, respectively. So we've got, for example, let's say an alkene like this. And then what you see is that we've got 1, 2, 3 bonds. So this means that the carbon of interest is a CH. Now, what you can see is that when I was drawing our saturated chains and unsaturated chains, the angle is approximately the same, and I'm drawing it as 120 degrees in both cases. So you represent tetrahedral angle as 120 degrees, even though, remember, it's slightly less than that. The reason for that is simply aesthetics. It's just easier to draw than 109.5. But with alkenes, we are actually sticking to reality because it is 120 degrees between your bonds. For alkynes, when you have a triple bond, however, we know that the angle in reality is 180 degrees, and that's how we draw it. Now, other guidelines for drawing your skeletal structures is to not draw any carbons, any hydrogens, or any CH bonds unless there is a good reason to draw them. So what's a good reason to draw your hydrogens, for example? Well, let's go back to an alkyne. If we have a bond that's at the end of the chain, that means that the alkyne is called terminal alkyne, then someone might think that you simply haven't finished your structure and that there might be another methyl group, so CH3, hanging around somewhere, and it's just not shown. So in order to indicate that it's a terminal alkyne, you need to show the hydrogen over there. And same if you are comparing a ketone with an aldehyde. If you draw your aldehyde like this, someone might think that it is a just unfinished ketone. Whereas if you draw your aldehyde with this hydrogen being shown, then people do know that you do mean your aldehyde. However, not showing your hydrogens is not really an issue in this case. It's just for clarity, and also when you are doing a lot of organic structures, it just looks better. And sometimes just by accident, you draw your 2 bonds coming out of your carbon, and then it's just easier to correct yourself rather than scrubbing all the images and starting all over again. Right. So now I would like to give you a small task to represent the following molecules as skeletal structures. It's just going to be 1 minute of you having a think about that. And then we're going to go through all of these. Here are the guidelines for drawing skeletal structures, just as a reminder. And I will go over that in 1 minute. All right. So if you had a go on at least one of them, well done. We are making progress. We are learning something. Let's go through all of them just to make sure that we are on the same page. So the first one, we see CH3, CH, CH3. What I like to start with, if I'm not sure about the skeletal structure, is to draw my molecule with bonds included. So now you can much more clearly see that this molecule, in fact, could be represented like this. Now, with the next one, CH2, CH2, so clearly carbons are not happy, they don't satisfy the octet rule. So it seems like there needs to be a double bond between them. So in skeletal representation, it will be just an equal sign. The next molecule, CH, I'm starting again just thinking about those atoms and assuming that these bonds are single bonds and then seeing what can happen next. We've got CH, C, CH2, OH. So here we are missing quite a few electrons, and the only possibility is when that's a triple bond. So what it would be like in a skeletal representations? Well, we've got our terminal alkyne. You can include your hydrogen or not if you wish. And then we've got CH2 and OH. Bear in mind that this is 180 degrees and this one is 120 degrees as said before. Now, with the last molecule, it's CH3COOH, which is in fact acetic acid, which you can find in your kitchen cupboard as vinegar. And in here we've got a CH3, so we start with one line and then COOH, which is a moiety that's standard for a carboxylic acid. Okay, let's see. So that would be a representation. Some people, you might come across some people representing your carboxylic acid like this, just to highlight that it is a carboxylic acid. However, in professional literature, people would usually just go for structure on the left. Right. So you might have seen that on the slide when I was talking about the tetrahedral structure of methane, we had those quite weird bonds popping up. And what do they mean? A wedged bond indicates that the bond is projecting out of the plane of the paper, in this case, out of the plane of the slide. And a dashed bond indicates that the bond is projecting into the plane of the paper. Yep, this basically dictates many properties of organic compounds. And instead of thinking about them as 2D structures, you now have to move to a 3D world and start thinking about them as 3D objects. Right, so let's now go to what we could do about those things. So if you have a 3D space, then it leads to possible isomers. And one possibility of isomerism is constitutional isomerism. So for example, when you have your butane chain, then you might have your methyl group just pointing straight from the carbon in the middle. And those are constitutional isomers because they have the same formula, but different connectivity. Another example of isomers are cis and trans isomers. So that one is trans, and the other one is cis. And you might find them called geometrical isomers in your textbooks. However, because we have the 3D arrangement around the carbon atom, stereoisomers, isomers with the same connectivity but different arrangements of atoms in space, are possible. An important thing is that the stereoisomers cannot be interconverted by rotation about single bonds. So one thing that I would like you to note is from this definition, different dispositions of atoms in space, actually geometrical isomers are stereoisomers. If you compare them, right? So they have the same connectivity, right? Those two methyl groups, CH3, 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 they are linked to the same double bond. And yeah, there is nothing that really distinguishes them apart from the arrangement of atoms in space. So it makes them stereoisomers, but a special kind. Because stereoisomers can be divided into enantiomers and diastereomers. Enantiomers are stereoisomers that are related as non-superimposable object and mirror image, which means that the non-identical molecules are related as object and mirror image. And those enantiomers, the molecules that can be enantiomers, or rather are enantiomers, are called also chiral. And it stems from Greek for hand. So if you see your hands, it actually helps you to remember what enantiomers are. So you have your hands, your thumbs are on the other sides of, well, on different sides of the hand. And if you overlap your hands, you can see that the thumbs do not overlap, which means that those two objects are non-superimposable. However, if you take a mirror image of your hands, then the right one will look the same as the left one, meaning your hands are enantiomers and therefore they are chiral. What does it look like when it comes to organic molecules? Well, let's go back to our tetrahedral carbon structure. And let's say we've got hydrogen, fluorine, chlorine, and bromine attached to it. And let's say that we want to produce a mirror image. So there we go. We've got our mirror image, and no matter how you rotate the molecule, you will not find any possible structure where these two molecules could overlap, meaning they are enantiomers. All right. So a carbon atom that has four different substituents, such as on the case that I just have drawn, we can call a stereogenic center or stereocenter or a chiral center. So in this case, we are talking about hydrogen over here. And also, if we have two same substituents, or if we can find a molecule that is superimposable on its mirror image, for example, your alkene, and we take a mirror image of this one, then we see that the mirror image is exactly the same as the original object, and therefore it is a chiral. Right, so enantiomers have the same physical and chemical properties in a non-chiral environment. So for example, if you have two beakers, you have one enantiomer in one beaker, the other enantiomer in the other beaker, and then you cannot distinguish them because they have the same physical and chemical properties. However, if you put an enzyme, for example, in there, then the enzyme will only react with one molecule. And this is actually also how our bodies work. Almost all molecules that are more complex than water have a chiral center, stereogenic center, stereocenter, if you wish, and then they interact within us differently. How chemists usually try to distinguish the enantiomers when they are, well, in this beaker. We usually try to see how they are rotating the plane of plane polarized light. And enantiomers rotate the plane of plane polarized light in equal but opposite directions, and it is called optical activity or optical rotation. And when we can see that the plane of polarized light is rotated, then the sample is said to be optically active. So I'm talking, all right, like there are enantiomers, same physical, chemical properties, different properties in a chiral environment. Why do we care? So there is an example of plus thalidomide, which was used to stop morning sickness, and it was introduced to the market, the U.S. market, in 1950s. However, it was introduced as a mixture of enantiomers. And the other enantiomer can cause fetal damage. And because of that, that they didn't notice that there are two enantiomers in that mixture, or that they didn't notice that the other enantiomer is basically a poison, there were over 10,000 cases where the pregnancies were damaged and kids were, well, dying basically because of the minus enantiomer. Maybe less tragic story is the fact that plus limonene smells of oranges, but then if you get minus limonene, then you would have a compound smelling of lemons. There's another example, minus carbon smells of spearmint, and then plus carbon has a smell of caraway and dill. So the properties, different properties can vary from being almost lethal to being nice smells. I mentioned the specific rotation, the optical rotation, optical activity. There are various names for that. However, One thing that's common is that they depend on many different things, and this value is not compound specific. So if you, for example, dilute your compound, the specific rotation will change. What won't change, though, is the sign. So each enantiomer will always have either plus or minus sign. What happens if you mix those together? You can see that same concentration, but yeah, just different sign over here and here. So if you mix one-to-one mixture of those compounds, you will get a mixture that's called a racemic mixture or racemate. And this one is optically inactive, meaning that it does not rotate the plane of plane polarized light. Another example where you don't rotate the plane of plane polarized light is when your compound is achiral. So non-chiral, it doesn't have a stereocenter, its mirror image can overlap with the original object. Right. So how do we actually test whether a molecule is chiral or not? So if a molecule or object has a plane of symmetry, it cannot be chiral. So for example, when we have our cis alkene, it has a plane of symmetry going through the double bond, but also you can have a plane of symmetry going through the plane of the slide. So we know that this molecule cannot be chiral. Now, if we have a compound with one stereocenter, so as we have shown this beautiful carbon with multiple halogens, then we know that this compound is chiral. However, this test is only reliable if you have one stereocenter, and if you have more than that, then your molecule might end up being achiral. So the only reasonable test for chirality is, in fact, the test of non-superimposability of the mirror image with the object. So if you can rotate your mirror image such that it 100% matches the object, then it means that the molecule is achiral. Right, so I'm going to give you another minute to determine which of these molecules are chiral. And just as a summary down here, the rules of chirality. Right, so let's go through all these examples together. So first of all, our first molecule has only one stereocenter, which is over here. Four different substituents on the carbon, so we already know that it must be chiral. So yes, it is chiral. Then we've got the second example, which might seem as chiral at first, but if you redraw this molecule, you can see that these two are the same, meaning that the carbon in the middle is not a stereogenic center. So this molecule is achiral. Then in the third example, you can clearly see that there is basically nothing, no atom which would point out of the plane or into the plane of the slide. So you have no stereogenic center here for sure. And it's also achiral. With the next one, what you need to check is whether it has any plane of symmetry, perhaps. And in this case, what we can see is that the plane of symmetry is going exactly through this bond, the red one. So you end up with a molecule that is also achiral. And now with the last example, let's just draw the mirror image of this one. It's a little bit tricky to draw, but with a little bit of practice, I'm sure you will get there. Okay, so we've got our bromine here, our hydrogen here, chloride here, and then methyl here. All right, so no matter now if we try to rotate it anyhow, for example, if we want to rotate it by 180 degrees in order to move a chlorine atom into the same position as in the original molecule, we would end up with methyl being like at the back of the molecule, which means that we are not getting the same image. So this one, in fact, is chiral. Right, so that's it when it comes to chirality. And then my Apple Pencil decided to die. Excuse me. Oh, yeah, okay. Hmm. Okay. Perfect. Right. So as I mentioned, stereoisomers are isomers with the same connectivity, but different arrangement or disposition of atoms in space. And we already talked about enantiomers, but I mentioned that also the alkenes can be termed stereoisomers. So what are they actually? They are diastereomers. Diastereomers are basically stereoisomers which are not related to each other as enantiomers. I'm seeing one question in the chat. I will discuss all of that at the end of the workshop, so please bear with me. So yeah, we've got diastereomers, and so in other words, all stereoisomers which are not related as non-superimposable object and mirror image are related as diastereomers. So remember the example of two alkenes, one cis, the other trans. So we've got our enantiomers. How do we describe relationships between them? Right, so if we have a molecule like this, and then we draw its mirror image, then the relationship between these is going to be enantiomeric. If we look at our alkenes in the top right corner, then we can describe them as diastereomers. And bear in mind that those those terms are mutually exclusive. Two particular stereoisomers are either enantiomers or diastereomers, but they can have different relationship with different molecules of a similar kind. Now, obviously, alkenes are not able to be enantiomers, but if we have, for example, two stereogenic centers in your molecule, then you can see where the diastereomers versus enantiomers are coming from. And another thing to mention is that diastereomers have different physical and chemical properties as opposed to enantiomers, which can only be distinguished in an achiral environment. Diastereomers, if you put them in a beaker, put some water, you can easily distinguish them. So bear in mind that diastereomers are different compounds. Right. So we know that in compounds with two stereocenters, let's just skip on a little bit. Okay, we've got, so let's just, as I mentioned, we can have molecules that have more than one stereocenter. And a good example is 1-bromo-2-chlorocyclopentane. Now, in compounds with two stereocenters, when the groups are not the same, there are always four stereoisomers. So we can name them A, B, C, and D. If a compound has more than that, then the maximum number is 2 to the power of n. So for example, if you have 3 stereocenters, then you end up with the maximum number of stereoisomers being 8. If you have 4, then suddenly it's increasing to 16. And if you have 10, then your numbers are over 1,000. So the arrangement of atoms that distinguishes stereoisomers is called configuration. So for example, A and C have different configuration on this atom. And same with B and D, different configuration here again. So let's go back to the example, 1-bromo-2-chlorocyclopentane, 4 stereoisomers. How are they related to one another? So there are two pairs of enantiomers. You can draw the mirror plane right in the middle. A is enantiomeric to B, C is enantiomeric to D, so we're all happy. Now, with B and D, there is no enantiomeric relationship between them. And also same applies to A and C. You cannot produce any mirror plane in order to flip the image. So what are those? Well, they are stereoisomers for sure, but yeah, if they are not enantiomers and they are stereoisomers, then it means that they are diastereomers. One thing that also we need to consider in terms of relationships is what happens on the diagonal. And if you compare the configuration on the stereogenic centers, so the atom arrangement on the chiral carbons, you can see that we also have a diastereomeric relationship. And same goes for another compound with two stereogenic centers. We have two stereogenic centers, 2 to the power of 2 is 4. So we've got 4 stereoisomers. And again, mirror plane goes through the middle. So we've got 2 enantiomers, and the rest is not related as enantiomers, yet they are stereoisomers. So we end up with diastereomers all over the place. So you can see that for molecules with multiple stereocenters, all stereocenters must be inverted to convert one enantiomer into the opposite one. Now, another case is when you have two stereogenic centers, but they look almost the same. So when we have, for example, our cyclopentane, but with two chlorine atoms attached to it, if we produce a mirror image of this molecule, and then if we rotate it a little bit, you end up with the same molecule that we were producing the mirror image of, meaning that this molecule, in fact, is a chiral because it can overlap with its mirror image. And the stereoisomer that overlaps with its mirror image is called a mesocompound. And also for that compound, you can see that there is a mirror plane going through the middle of the carbon-carbon bond adjacent to the chlorine atoms. However, there are still more possibilities in terms of the configuration on the stereocenters. So you can have one chlorine pointing down and one pointing up. And then let's just produce a mirror image of this one. Which is like this. Right, if we now try to rotate the molecule a little bit, just to try and match it to its mirror image, what we'll get is one chloride pointing up and then the other one pointing down. And if you try to flip it, then yeah, you'll basically still get the same molecule as this one. Meaning that because of some rotations, we do not produce the mirror image, meaning that those two isomers are chiral. And they are enantiomers. So one thing, they are enantiomers. Okay, cool. But there is still that top molecule that we need to compare it to. So as before, there is no enantiomeric relationship between, for example, these two species, but they are still stereoisomers, meaning that they will be diastereomers. And same goes on the diagonal. We again have diastereomers. So yeah, just to repeat, the compound with a mirror plane or a stereoisomer with a mirror plane is termed a mesocompound and is a chiral, meaning it doesn't rotate the plane of plane polarized light. So just to sum up, what are the isomers that we can have in chemistry? First of all, the general isomer is a compound with the same molecular formula. We can have constitutional isomers, same molecular formula, but different connectivity. Stereoisomers is a different class. We can have same form molecular formula, same connectivity, but different arrangement of atoms in space. And those can be divided into enantiomers, stereoisomers, which are related as non-superimposable object and mirror image, and basically everything else. So that's everything.